Hello everybody to the 3D scanning and motion capture lecture. Today we're going to talk about optimization methods for 3D reconstruction. So as usual, I'm going to start with a quick recap of what we have done so far. So at the very beginning we talked about how do we obtain 3D data. We talked about different sensing devices, specifically depth sensors, time of flight, stereo, laser, LiDAR, and so on. And afterwards, we talked about once we get this kind of data, what is actually the representation we can use in order to represent 3D surfaces, 3D point, and generally speaking, all kind of 3D entities in this case. We talked about point clouds, we talked about voxels, polygonal meshes, parametric surfaces, and specifically implicit surfaces. We also talked about how can we go from between these representations, right? We talked about how we can go, for instance, from point cloud with Poisson surface reconstruction to a polygonal mesh. We talked about how can we go from implicit surfaces with, let's say, marching cubes and raycasting to either depth map or an explicit mesh representation. And then we continued actually already looking a little bit in the reconstruction. Specifically in the last lecture, we talked about correspondence finding and correspondence matching. We talked about what kind of features one can use, handcrafted features or learned features. We talked about the whole idea of bundle adjustment, right? So once we have these kind of correspondences, we have kind of this correspondence graph. We have these tracks of correspondences across the multiple input frames. And then we talked about the math behind the bundle adjustment formulations, which essentially leads to the structure for motion problem, where now what we're doing is we can optimize for the reprojection error, right? So for instance, here in this case, we have two images, right, the left and the right-hand side. And we're trying to make sure that in 2D we can optimize for this reprojection error and minimize it. And we're optimizing for the camera transformations for the left and right-hand camera here and for the respective 3D points. And this is probably a pretty important slide here because it has basically all the important parts on it. It's mathematically not super complicated, right? We have here our intrinsic camera projection, we have our extrinsic camera poses. This is our point in 3D that we want to optimize the X, Y, and Z coordinates for. And here are the respective images, right, where we have observed the feature correspondences. And now we're going to essentially solve this minimize this energy term. And of course, we're not going to do this just with two images, but in fact, we're going to do this with many images. In fact, we have here m images, we have n points, and then we have this bundle adjustment formulation here, where we're trying to solve for all of the t's and all of the x's at the same time. Sometimes, again, sometimes also we are solving for the intrinsics for the cameras. In this case, I left it out because for the most part, what we're dealing with here, we're actually not going to do that. But I just wanted to make sure that in bundle adjustment, generally speaking, you can very well solve for the intrinsics when they're not available. Often they are, though. It depends a little bit. Okay, and then we talked about how the whole thing looks in RGBD. When we have depth as input, then the bundle adjustment formulation becomes a little bit easier, right? So now here we're having points in 3D already given, because for every pixel where we have a correspondence, we have a match, and we also have the respective depth value, so we can compute the 3D piece here, the 3D points in camera space, by back projecting the depth value. And then we're optimizing this term here, where we have two loops. One goes over the correspondences, one goes over the frame pairs, ij, and we're optimizing for the respective t's. And note that in this case, the formulation is a lot easier and simpler to solve than in 2D. Because we don't have to solve for the points x here, and we only have to solve for the respective transformations t. And then in the end of the last lecture, we looked at these, which looks a little bit complicated terms, but in practice they are relatively straightforward. So we have this dense depth term. So we're doing the same thing. We're saying between all frame pairs, we're summing over all the pixels that overlap between those respective frames in a frame pair. And then what we're doing is we're checking for a given point in one of the two frames, we're transforming it to the other frame, we are projecting it to the respective image space in that frame, we're looking up the depth value, we're projecting this point back to 3D in camera space, and then we're projecting it back to the original frame, and then we're comparing it. Ideally, we get the very same point here, right? And the idea between this formulation here is that this one now basically considers every single point, right? And what you're doing is you're doing direct lookups in the respective depth values, and this actually is a formulation we're going to use later on also for point-to-point and point-to-plane alignments. And there's this little detail here where we have the normal. So we don't just take the closest point when we're projecting in the respective other frame, but instead we're taking the dot product with the normal, meaning that we have kind of a planar surface approximation in that local area, and we'll later see why this n here makes sense, because that's essentially a point-to-plane term, which we're later going to see when we're talking about ICP variations. We talked about doing the same thing with a dense color term. So dense color term, same idea. We're having a point in one frame, projecting it to the other point. Instead of looking up the depth value, we're now looking up the color value in that frame. We're checking out the image, what the color value is, and we're comparing it with the color value in the current frame. And we're typically taking the gradient here because that's a little bit more stable. We'll talk about this a little bit later, why you would use a gradient rather than the absolute color values. But then basically it's the same idea, right? We're just minimizing the photometric error between those two, and we're optimizing for the t's. Now, what you can do is actually in practice, right? This is something I haven't said last time yet. You can actually go ahead and take all of these three terms in principle at the same time and can jointly optimize for all of them. One thing we will realize, and we'll talk a little bit more in detail in it, is typically you want to start with these ones here first, because that's the one that has the best optimization properties. Then you probably want to add the depth terms, and then you want to add the color terms. So from pure complexity and difficulty of the energy landscape, this one here is the nastiest one in a sense, because photometric alignment typically is very non-convex, and it's very hard to optimize for, because you just have so many local minima that are important to consider. Okay, today we're going to talk about the optimization methods itself. To me, this is a very important task, because I think if you want to do research and have an academic career in these areas, like knowing the underlying optimizations is really, really, really important. This is just so fundamental. And what's also important is not just knowing one optimization for one specific problem, but it's important to know for which problem, which optimization might make sense, and why and how you actually implement it in practice. And I should also highlight, I know that a lot of these optimization methods people have already heard of in some sort of intro math class in the undergraduate. But the honest answer is, my experience right now is that a lot of students just forget it, including myself probably. When I was a student, I also had intro math classes, and I never realized the significance of many of these optimization methods until I actually had some real problems to solve, and then I basically had to learn it from scratch again. So this is kind of I hope that this is, in a sense, on one hand, it's a bit of a refreshing course, on the math side, but on the other hand, I also want to make sure that you know for which problem, which optimization is suitable, and you can actually, we can talk about, reasonable scientific terms when we're talking about how to address these issues. Okay, so let's start simple with the simple terms first. Let's say we have these two prominent terms. I'm not going to go into all of them, but I just want to say which terms do we have. Okay, so we have bundle adjustment. This is the standard 2D version, right? And we have only Rgb input. We're optimizing for the reprojection error, which is these are basically these are two residuals each in 2D, right? It's just the x and y coordinate of every matched point. We are optimizing here for t and for x, and we have a sum over a lot of these correspondences that we have found in practice. In 3D, again, it's a little bit easier, or in the Rgb case, it's a little bit easier because, again, we don't have to optimize for the x's, we only optimize for the t's here. But still we have two loops here. One goes over all frame pairs, one goes over the correspondences between each frame pair, and then we have a bunch of key point correspondences essentially that we have to minimize. And again, note that these are in three-dimensional space now, so we have three residuals in each of these loops. And these terms here, as you can see, they are square terms. They're actually non-linearly square terms because there's a nonlinear part in it. But all of these are a sum of square terms. And this is typically the form what you have in bundle adjustment problems. And I want to talk a little bit about least squares. So this is actually very fundamental, and it's not just applicable to these kind of things, but you really need to know least squares in order to figure out what are the right solvers here. Okay, so if we are talking about least squares, right, we have a function f of x, and we just have a sum of squared residuals, right? So we have a bunch of residuals Ri. These residuals are dependent on the unknown x, respectively, and these are squared residuals. And again, if you're going back here, right, these two here, they are least squares problems, right? There's a bunch of sums here. Each of these are square terms. And what we're trying to do is we're trying to find the optimal solution of the respective unknowns here, such that this term here is minimized, or this term respectively. Okay, but going back, we have here the sum of the squared residuals. And often what you see is you see this kind of short notation with the 2 norm, right? So you're writing it like this. So we see, okay, what we have is here we have this residual vector f here, and this vector here has a bunch of residuals stacked in it. And you can, well, these are actually squared based on the norm done, right? And again, this is just different notation, but it's mathematically the same thing. Okay, one thing what is really important, I'll get to this in a second if you're going back quickly here. Note that this sometimes might be a little bit confusing because each of these sum entries here, they have actually 2 residuals, one in x and one in y direction. And here we have 3 for each sum, one in x, y, and z direction. I'll get to this later, why this is actually really important, why we need to consider them as independent and separate residuals. Right, but again, conceptually very straightforward. We have a sum of square terms. We have, or we write it down as this like residual vector f, and we have these residual terms attached to it. And now our goal of this least squares is that we want to find the optimal x such that this function f of x is minimized, right? So we want to find the optimal version of x. This is our goal, what we want to do. So yeah, so f is this like is the stacked vector of residuals. We have the sum, but this is the easiest way you can imagine it, right? It's just the sum of squared residual terms. Okay, now I wanna start with a very simple example of least squares and how you would solve them. And in fact, many of these things you probably should already know. Even in high school, I think people doing this. The simplest thing you could imagine is a least squares problem, right? That is linear. And in this linear least squares problem, you know that each of these R terms, I'm going to go back quickly here, each of these R terms are just linear functions and have no nonlinearity in it. So let's talk about a simple linear least squares term, which is we just want to fit a line here to a set of data points in 2D, right? So in this case, we have this linear function, which is it has basically 2 unknowns. The unknowns are m and t, right? These define the line equation in 2D. And when you're feeding in an x and y are the respective data point pairs, right? So x and y, if I put any of these blue points into this equation, I would like to have them all on the same line. This is what I'm trying to solve right now. And the unknowns are, in this case, are m and t, and x and y are the respective data point pairs. These are the blue dots, right? Okay, so we want to solve for m and t. So each of our, so let's do it in the least square sense, how we just did it. So each of our residual terms, Ri, have they're dependent on the very same 2 unknowns. They're all dependent on m and t, right? And all we're going to do is we're just going to use our linear function here, and we're just going to say, well, yi, my current data point, minus m times xi plus t should be equal to 0, right? This is what I want to do. I want to make sure, ideally, I would love to make sure that this is always 0, and I would like to make sure that each of these terms are actually all 0, right? So every Ri here corresponds to one of the blue dots. So every Ri gives us one residual term, right? It's very straightforward, but when I'm going to talk about this, I will always tell you, oh, look at the residuals, how many do we have? And look at how many unknowns we have. In this case, we have 2 unknowns, m and t, and we have residuals, which is equal to the number of 2D points that we have here. Okay. Now, what we see very quickly, if we make this a very concrete example, we see we have a bunch of blue dots here, and they're not actually all lying on a line. So we already will see that, oh, it's actually not possible that they're all lying on this red line. We can't construct a line that like covers all points. So we have to find, we have to solve this problem in a least square sense. This is where the least squares comes into play right now, because as you see here, there's no squares right now, right? There's no square. But I'm going to introduce the square right now, and this comes via the normal equations. So let's make this a practical example. All right, let's again say we have these residual terms. Let's say we have 4 points. I want to make this very concrete, that you can actually go through it and understand every single step. And I know it's easy, but I think it's really important to understand the concept of least squares. Okay, so we're going to have 2 vectors here. So each of these are points. So we say 1 and 6 is one. This is one data point. 2 and 5 is one data point. 3 and 7 is one data point. And 4 and 10 is a data point. So we're having 4 points in 2D that we want to approximate with our least square solution, and we want to fit this line such that these points ideally are on the line. Again, we already see that this is not possible because with 4 points, they might just not lie all on a line, right? This is one of the issues. But let's see how we solve this in a least square sense. Well, the way we do this is we say we go through the normal, we put these ones here into a matrix, right? So the way you do this is we know, okay, B is our residual term here on the right. We're just writing this in matrix form right now. We're just writing A times X is equal to B, right? I just want to write this whole thing as a matrix. And the way you want to write this as a matrix is you just look at this equation here. So this equation is going to tell you, oh, M times X. So the M's are going to be here, right? These are the sorry, it's not right. So X is this one here. This is multiplied by M. This goes into the matrix here, right? Because we have X here. This X here is M and T, right? This is M and T. So I'm looking forward to what are the coefficients here for M. These are the Xi's. These are these coefficients. Then I'm looking what are the coefficients for the T's here. These are always 1. This is why this matrix has 1, 2, 3, 4 from the X, which is multiplied with M. And again, this X vector here is M and T. This is this vector here, right? Just so you know. Okay, so X here is M and T, and we know A has to be multiplied, so I'm just going to write this form here as a matrix. So we know here we have the Xi's, and here for the T we have always 1, and here we have the Y's that are respectively on the right hand side. Okay, and as we have already discussed right now, this is an overdetermined problem, right? We have more equations right now in this linear equation system than we have unknowns. In fact, we have 2 unknowns and we have 4 equations, right? It's very straightforward because we had here 4 data points, and our line that we want to fit only has M and T, so it only has 2 unknowns. Okay, so now what we want to do is we want to solve this whole thing, and the way we do is we solve it via the normal equation. And this is basic linear algebra. So what we're doing right now is we are multiplying both sides with A and AT, right? And this is where the square comes into place. Now this is becoming a least squares problem because we're solving this in a least square sense, right? So in other words, what we want to do is now we want to basically minimize, if you're going back here, if you're looking at this problem with this line here, we want to basically make sure that in a least squares sense, we're finding the optimal line such that the least squares error, i.e. the distance here to this line, is going to be optimally distributed in a least squares term, right? And this is what you do via the normal equation. It's very straightforward, actually. So you just multiply both sides here with AT. And if you're doing this in this very concrete example, this is what we're getting right here. We're having like ATA is 30, 10, 28, 4. ATB is 77 and 28. So note the importance right now. What happens is if you're multiplying A with AT, you're getting a square matrix, which makes sense, right? Because if you take A transpose, right? So A transpose is going to be a 4 times 2 matrix, and you're going to multiply it here with a 2 times 4 matrix, right? And this is going to give you a 2 times 2 matrix at the end. Same thing for B is, if you're multiplying B here with AT, you're going to get a two-dimensional vector as output. And now this is a square matrix, and now this least squares problem here, these normal equations, or this normal equation, this one actually is a well-defined problem because we have two unknowns and we have two equations, right? Okay, and now what we can do is we can take this matrix here, this linear system here, and we can solve it with our favorite solver. I'll get to this in a second, what the favorite solvers are, but this is very straightforward now, right? We have two equations and we have two unknowns. We solve it respectively. We're going to get our optimal values for M and T. This is what we're getting at the end of the day. Okay, so here's one interesting thing, right? So the idea of the least squares solution here is, if this already had been a 2 times 2 matrix, then multiplying the 2 times 2 matrix again with the 2 times 2 matrix will give you actually the same optimal solution, right? So this is kind of the idea, that in the case where you have the same number of unknowns as equations, the least squares won't change anything. It's going to give you the same optimal result. But here we have the opportunity that when we have more or even fewer equations than unknowns, you could still solve it in a least square sense. Okay, I'm not going to go into all the details behind it. I'm actually pretty sure that pretty much everybody probably, if you have heard of this kind of stuff, may have forgotten it, or even maybe you still remember it. So either way, I think at this point, I hope you still understand what least squares means, and I hope that you understand what solving a least square sense means. Okay, so now this is of course a super simple problem, and the simplicity in this problem is, on one hand, of course, we have only two unknowns, but the other part is this here is linear. And now we want to see, I guess we can see a few more examples first before we move ahead. In the linear part, linear doesn't mean that it's just such a simple problem. So for instance, if you want to fit a quadratic function here, right? You can also do it this way. You can just go ahead and have the quadratic function y is equal to ax squared plus bx plus c. You can now solve for a, b, and c. Now we have three unknowns, and it's actually linear with respect to a, b, and c, because if you're writing this down as a matrix, you're gonna know, okay, you're just going to write down your data points here, right? So you have the points for A, B, and C. This is going to be our x vector. So this x vector is A, B, and C. This is what we want to solve for. And then we're just writing down from this equation here, we're just writing down the linear coefficients. And in this case, the linear coefficients for C is always going to be 1. The linear coefficients for x, it depends on the points now. That we're having is, in this case, we have 0.11, 0.42, 9.3, and so on, right? Okay, so we can write these ones down as a matrix form as well. We have here our residuals B again, same idea, right? We have respectively what our y points would be. We know, right? So this one is 1, 1, 1, 4, 2, 9, 3, and 16, 4. This is just the squared version of the coefficients here. This one is the respect of these are the x values basically, and these ones are the y values. And now we have the same thing. Now we have 4 equations, we have 3 unknowns, and we solve it via the normal equation, right? So it's very straightforward. Okay, yeah, so this is just another example. I just wanted to make sure that fitting to a polynomial here, to this quadratic function, is actually also linear, because the only thing what you need to do is you have to check, is it linear with respect to A, B, and C. And with respect to A, B, and C, it's actually linear. The only thing what you have to do is you have to pre-square your x values here, right? And because of that, it's still linear. The y is obviously linear in this case, right? And then with respect to A, B, and C, this is a linear function, a linear system, and you can solve it accordingly with our normal equations. Okay, so let's talk a little bit about how we can solve them and what are good solvers. I don't want to go into all the details how each solver works. But if you haven't heard of this in a long time, then you might want to look it up. like I think of this more as a reminder that, hey, by the way, these solvers exist and you should roughly know what they're doing. Okay, so if we're talking about solving this normal equation, ATAX is equal to ATB. And this is kind of funny because whenever I have an interview for PhD students or even in our startups or so, and when I'm asking some technical questions, I'm typically going to ask people, hey, how do you solve a linear system? Or how do you solve a linear equation like AX is equal to B? The first answer I'm getting is typically I'm going to compute an inverse. And the second answer I'm going to get is a gradient descent. And both of these answers are terrible. And so the inverse is terrible for large matrices. It's numerically not very stable. And it's also terrible if you have a sparse matrix. The inverse is not going to be sparse anymore. And most of the time you have some sparsity you can actually exploit. So computing an inverse for a large equation system here is in practice a really bad idea. If you have a 2 times 2 or 3 by 3 matrix, you're welcome to compute an inverse. That's not a big issue. But if you have like a million times a million dimensional matrix, please don't compute an inverse. Not a great idea. Gradient descent is also a really bad idea. Gradient descent, the first thing when I say I have a linear system, like A times X is equal to B, people are really confused when I ask them, so what's the gradient of a linear system? And then they're confused. So in principle, you can actually compute a gradient out of a normal equation, right? I just wanted to mention that. So in principle, this would work because this is a square term right now, right? And from the square term, you're going to get actually a gradient, and you can do gradient update steps, and in principle, you could solve that. But from a convergence standpoint, from an efficiency standpoint, it's a really, really bad idea. So this is like the worst answer in a sense you could give if somebody asks you how to solve a linear system. You say gradient descent. First of all, you have to know the normal equation stuff. Otherwise, this makes no sense at all. And even then, it's not the right answer, right? Because it's just not the right thing to do. Okay, now let's talk about the things that we should actually do. And by the way, gradient descent is the thing that everybody hears as the only solver in deep learning. This is why people say it all the time. This is the main reason right now. So yeah, you have to be a bit better than this probably now. Okay, but let's talk about how we actually solve it. In principle, there's two types of approaches. One of them is iterative, and the other one is well, it's direct, but direct means more or less you compute some sort of factorization of the matrix that makes the problem easier to attempt. So if you're talking about iterative solvers, basically these three are the main ones. So Jacobi, Gauss-Seidel, and conjugate gradient descent. So CG or PCG for preconditioned conjugate gradient descent. These are good solvers for linear systems. In practice, everybody here would use PCG. I'm calling it PCG because it's preconditioned conjugate gradient descent. This is a solver that a lot of people are using. And the direct approaches is basically QR decomposition, LU decomposition, Cholesky decomposition, SVD. These are things you should probably know. I mean, I would probably expect that you know how SVD works, right? So these have pros and cons, which ones to use respectively. Depends a bit on the problem setting, like which ones work better. But I think it's really important that you have a rough high-level overview of these methods. So if you have never heard any of these things, I would highly recommend look them up. Typically, I think these should have been all introduced in a linear algebra class. Okay. Again, don't know it. Please look it up. Really important, actually. But I don't have the time right now to go into all of them. But I wanted to have this as a bit of a refresher course that these are really important solvers for linear systems. Okay. All right. Another thing that's always interesting is so when I was teaching like intro numerics or stuff like this, I always ask students to implement your own solver, and this was always quite interesting because it's practically speaking not easy to write one of these solvers yourself. It's really difficult actually, and the reason why it's very difficult is for mostly numerical stability. I mean, there's scalability and efficiency. It's not easy, right? Being fast is important, but the numerical stability to solve large-scale systems with your own implementation of a solver is not so straightforward. And often you need a lot of tricks. Like one thing I already mentioned briefly was this preconditioned conjugate gradient descent. So preconditioners is another thing that is important. So preconditions are basically ideas that you apply to a matrix in order to get the condition number down. And then you kind of reverse solve it afterwards and resubstitute it in. There's many different ways how you can do good preconditioning. That in its own is like a whole lecture probably, how to do it right. But I think what I'm trying to say is that if you have to implement a solver yourself, it's actually really difficult to do it right. It's not so straightforward. Numeric stability is one thing. Scalability is another thing. Efficiency is another interesting version. So in the age where a lot of people are used to Python coding, sometimes people don't understand anymore how real compute processors work and what compilers are actually doing under the hood. So most of the time, you know, you call like, I don't know, like NumPy or so, like the linsolve or so, that works. It does something reasonable under the hood, but somebody had to code this in a low-level language, probably C or C++, in order to make sure this stuff runs, and it works really well, right? So like, don't be fooled that most of these libraries in high-level languages, and I'm on very high-level languages like Python or so, right? These solvers under the hood, they are still very sophisticated in what they're doing. They're just abstracting it away to make it easier for you to use. But here's my recommendation again. If you want to actually use a solver for your real practical problems, such as 3D reconstruction, use existing solvers, right? Don't try it on your own necessarily right away. There's very good solver packages you can try out. I wanted to give a few examples of what people often using. So there's Eigen, Tox, Umfpeg, QSpars, but there's many more. I mean, I just put this comparison here. And these ones are really, yeah, really like in-depth numerical knowledge. They're really rock solid what they're doing. I mean, I originally come from a, you know, like C++ background. I did a lot of stuff for like bundle adjustment and so on, and 3D reconstruction. So I use Eigen a lot. So Eigen is a really cool library. If you want to learn more about programming, Eigen is a really good way to look it up. It's not easy to understand at the beginning internally what they're doing, but they really know how to use C++ template magic. And that means basically a lot of the things like matrix sizes and so on, they're all templatized, meaning that the compiler knows at compile time what it can optimize away, like can unroll a loop and stuff like this and so on. And they have a lot of expression templates and so on, which is really fancy. And it's really cool. So I actually learned a lot when I looked at Eigen and the code. And I think it made me actually a better programmer at the end of the day. But if you also just want to use a linear solver, Eigen is really good and really efficient for a lot of the problems that, for instance, we're dealing in this course with, right? Okay, so these are a couple of things I would recommend. Have a look at Eigen. Eigen is just a really cool library. A lot of people use it. It's great. Very fancy in terms of how it's implemented. You can learn a lot there. But on the other hand, you can also just use it, and it works pretty well. Okay, so now we've talked a little bit about linear solvers. And now we want to go and make the problem a little bit more complicated. Now we want to go to nonlinear squares, right? So nonlinear squares, from a high-level standpoint, they have the same idea. They have a function f of x. It's a sum of squared residuals. Nothing different than before. We still want to find the solution that minimizes this sum of squared residuals. Again, same as before. And the only difference there right now is, and this is an important difference though, that Ri is now nonlinear with respect to x. Right? And this is the important part. And this, of course, makes the problem a lot more complicated. And I wanted to talk a little bit about how to approach it and what to do with it and show you a few examples first. As a quick hint already, nonlinear squares problem is basically everything we're dealing with right now in this lecture. Like all the bundle adjustment stuff, all nonlinear squares problem, right? So most of the time you have a rotation matrix somewhere, and the rotation matrix is nonlinear with respect to x, right? That makes the whole thing nonlinear. But let's start with a simple thing. Let's start with a simple example. let's just say we have a bunch of 2D points, these red points here, right? And what we would like to do is we would like to go ahead and fit a Gaussian curve to these points, right? The line we've done before, the linear thing, it's a bit boring here, like fitting a line to these red dots might not be ideal. So now what we might want to do is we want to fit a Gaussian curve to these points. So how do we define a Gaussian curve? Well, we have this function m here. This is our kernel in this case. And what we have, we basically say, well, we say we have here x1 times e to the power of minus t minus x2 squared divided by 2x3 squared. Now, the important thing right now is look at what the respective unknowns are. The respective unknowns in this case is x1, x2, and x3. These are the things that define the parameters for this Gaussian curve. If I have x1, x2, x3, then I know this Gaussian curve, and then I know whether my points are on this curve or not. So now the residuals here are going to be Ri with respect to x. This is like the query point that I have. So I'm going to say yi minus this function here of x and ti, right? So it's relatively straightforward. This is probably the simplest case of nonlinear squares. And now what we're trying to do is we're saying we have all of these points. This tells us how many of these residuals we have. So we have these points of yi and ti pairs, right? Like yi and ti are the respective 2D point pairs. And our x is what we're trying to solve for. These ones we have exactly 3 of. This is defining our Gaussian curve. So what do we have? In this case, we have a bunch of red points, and we're trying to solve respectively for our Gaussian parameters. Now, importantly here is we have 3 unknowns right now, but we still have a lot more equations than we have unknowns actually. So this is still an overdetermined system. In practice, well, ignoring the fact right now for nonlinear problems, for the most part, there's no analytical solution anyway, even if it's not overdetermined. But for the most part, when we're dealing with problems, we always want to have more residuals than we have unknowns. And in practice, we want to have significantly more residuals than we have unknowns. We'll talk about this in the bundle adjustment problem, or we have talked already a little bit about it. But whenever you're dealing with these problems, you have to probably make sure that in this nonlinear squares problem, you have more unknowns and significantly more unknowns than, sorry, you have more equations, significantly more equations than you have actually residual, you have unknowns, right? More residuals, few unknowns is good. Okay, so now this is a common example. Now, how do we solve it? Now, there's a bunch of different versions how to do that. And I wanted to walk you a little bit through what are good choices when we're approaching it. Okay, so these nonlinearly squares terms, again, they're written down like this. It's straightforward from a notational standpoint. You can write it down with our norm notation, right? So we have same thing, argmin x, f of x. This is our sum of nonlinearly squares in this case. And we're trying to find the optimal x here, right? Okay, how do we do it? Well, the simplest thing here is using gradient descent. And here gradient descent is actually the right answer because it's a nonlinear problem, right? So what do we do here? Well, we have our function f, right? We're computing the gradient of x, of f with respect to x. We're taking an initial version x0 here as our initial set of parameters. And we're computing the gradient, and we're just updating our parameters in our gradient direction. Nothing fancy, right? So we're just saying we have a set of, we have xk here, that's our current set of parameters. We're computing the gradient of the function at this point, and we're just updating the parameters going according to the gradient direction. And we have a step size t here that's telling us how long should we go into this gradient direction. Then we get an updated step, and then we repeat this whole thing, right? This is gradient descent, so we repeat. In like deep learning land or machine learning land, this t is often called the learning rate. We're not going to call it the learning rate. We're going to call it what it is. It's just a step size in gradient descent, right? So this is the right thing to call it. Okay, this is the easiest solver to implement. It works, nothing wrong with it. Practice often it's a bit slow, depends on the problem, of course. So there's better versions to do that. And one better version to do it is to think about the order of approximation. So what I mean by the first order here, this is a first order solver, meaning that it just computes the first derivative here, right? And based on this first derivative, it just assumes, oh, locally, my gradient is just going to be linear. What does it mean? Well, I'm just saying, like, okay, I have a nonlinear function, and I have a linear approximation locally of this function. So my gradient is just a line, right? I'm just assuming locally my function is linear. I'm doing a step there, and then I'm reevaluating the gradient, and I'm again like thinking it's locally linear, doing a step, and so on. This is called first order, right? And now, of course, when there's a first order thing, you can also do a second order thing. And this is the second order method that we're going to talk about is Newton's method. So here what we do is we actually going ahead and saying, well, we have now, here's the first order derivative, and here's the second order derivative, and we're taking both of them into account. So we're not only considering how I have this linear approximation locally, but now I'm approximating my function with a second order term. And the second order term comes from the second derivative. And the way this works is now we have the gradient of f of x at this point. We compute the Hessian at the same point x, and then we're computing the inverse of the Hessian. I'll talk in a second. We're actually not computing the inverse, but like mathematically it's the inverse. And then we're subtracting this from xk, and then we're getting an update step. Now, the difference of the second order method here is that we're basically assuming locally the function is approximated as a quadratic function, right? And this makes a lot of sense in the context of nonlinear squares because we have local square terms. This is why Newton's method with the second order solver in practice works a hell of a lot better, right? And there's a few catches still. We have to still talk about it. But I first wanted to understand what the difference between, like mathematically speaking, first order and second order methods are. Another way to think about it is, if you're thinking about it, I don't have a slide right now for this, but basically what it does is, if you're thinking about a Taylor expansion. So a Taylor expansion is approximating your function with a series of the derivatives of this function. Gradient descent is taking the first order approximation of the Taylor series. Newton's method is taking the second order approximation, right? So you have here the second derivatives are also in here, right? That's the difference. So yeah, if you want to derive your Taylor expansion, it's the way to go to look at, and then you know how it goes. And again, especially for these squares terms, this one makes a lot of sense because these are local square approximations. Okay, but let's have a look how it actually looks a bit in detail. Let's talk about gradient descent first. Often gradient descent is approximated with GD. That's what people do. We take the gradient. So we compute all the partial derivatives here of our vector. So we, for every, so basically for our function f, we're computing a partial derivative with respect to x1, with respect to x2, with respect to x3, and so on, right? So we need to compute these partial derivatives. You can do this. I'll talk about this in a second, how we do this efficiently, numerically speaking. And then we have a gradient, and then we taking our current initial set of parameters, we're subtracting gradient times t. And the second thing we have to do is we have to determine this step size. Sorry, the typo, this has to be step size. This is not a set size, this is step size. And there's a couple of ways how to do this properly, actually. Line search is one thing. So line search basically does, you're assuming you have a fixed gradient given. You're assuming this locally now my function is linear. This means that I'm looking at this, I'm taking the gradient as a line, and I'm going along this line, and I'm finding where in this line has my function, or where has my energy term the smallest value, right? If you're doing line search properly, and you have a linear function, then this would converge in one step. It's not the most efficient way to do it, but that's just practically what would happen, just for your own understanding. Okay, there's a few more fancier things here. There's things like momentum. So you can track the history of gradients, so you have a better estimate how the gradient is going to develop. Basically, if the gradient has always been the same, it makes sense to accumulate gradients, and then you just go faster or do larger steps in a certain direction. That's basically momentum is. And there's a couple of different versions of this. There's also a lot of theory, right? You know how to set these step sizes and so on. Okay, but idea is relatively clear, I hope. We're basically going to go ahead and say we have a first order approximation, right? So the gradient, we just assume locally this function is linear across its gradient. We're stepping across the gradient, and then we're reevaluating the gradient and so on. You just iterate the process. So it's relatively straightforward. Okay, now let's talk about Newton's method. And Newton's method, again, this is a thing you should actually already know in high school. This is this funny animation here. Newton's method in practice is doing root finding. Root finding means, well, we're saying we're having a current initial value where we're trying to find the root of the function. The root is basically where the function intersects with the x-axis, right? Where the function is 0, right? And then what we're doing is we're saying, well, we evaluate the function at this initial value, f of xk. We're computing the slope there by computing the derivative, dividing the function value divided by the slope, and we're subtracting it from the function. And then this process we're iterating. And this is what's visualized here. So I copied this fancy animation, and I wanted to show you what this means. Okay. So we start here, evaluate the value, compute this tangent, intersect it, check here the value again, compute this tangent, get this value, compute the function value, compute this tangent, and so on, and we iterate. And this is Newton's method, how we're finding roots of a function. And I'm pretty sure this is a thing that people learn in high school, right? You can do this geometrically very easily. It's very easy to comprehend. You can also do this in higher dimensions, of course, but in 2D it's just very straightforward, right? And when you iterate this, you will converge and will find the root of the respective function. Now, how does it help us in order to optimize a nonlinear squares problem? Well, that by itself doesn't optimize a least squares problem, but let's put it differently. If we want to go ahead and we want to find the optimal, or we want to find a local minimum of a function, what this means basically is we just want to find where's the derivative of the function 0, right? So we want to find the root of the derivative. Well, right, like when you do optimization, the first thing you do is you set your derivatives to 0. And that's essentially what Newton's method for optimization is doing now. So what you do is we're checking out our root finding, right? So we say, okay, we have a function f, and we know how to find the root of this function by doing this iterative Newton process. And now what we want to do is we want to find the root of the derivative. So we simply say, oh, we want to find the root of f prime of x, and then this just becomes the second derivative, right? So we compute the derivative of f prime, which is the second derivative of f, and then we do the same thing. And this is what we're doing for Newton's method here, right? This is Newton's method for optimization. But yeah, maybe don't confuse it, right? So standard Newton is actually just root finding, and then what we're doing is we're just using it right now to find the root of the derivative. So in 1D, this is very straightforward. This is just what we have seen. Now, of course, we are not in 1D. We don't have just a single 2D problem. We actually have very high dimensional problems in practice. And so this is essentially what I just tried to explain. This is Newton's method. And now this first derivative here becomes the gradient, and the second derivative here becomes the Hessian matrix. And like dividing by the Hessian matrix means we have to invert the Hessian matrix. So it's the inverse of the Hessian times the gradient of f of x, right? And then we can iterate, right? This is Newton's method for optimization. It's very straightforward, actually. Let's do a bit of like let's have a look a little bit what this means actually. So now, a few things that we have seen here already is we need to compute gradients and we need to compute Hessians. How do we do this in practice? Well, in practice, let's talk about the first thing. So when we're talking about the gradient of f of x is actually the same as 2 times the Jacobian of f times the respective function values. Right? And the Hessian is, well, it's the Hessian matrix, right? Okay. Well, the Hessian matrix is the Jacobian of the gradient, of course, but the Hessian matrix, let's talk about the Jacobian first. So the Jacobian basically has the partial derivatives, right? So you taking here, you have a matrix that has the rows here are the number of residuals, and the columns here are the number of the unknown variables that we solve for, right? So we have here the first residual with respect to the first unknown, the first residual with respect to second unknown, third residual, and so on, right? This is like, this first row here is always taking the first residual, and it's computing partial derivative with respect to every unknown that we have. And then the second row here would be the second residual, again, computed partial derivatives with respect to unknown that we have, right? And so on. And this gives this matrix that is residuals times number of variables. And what we can do now is we can compute this matrix of the Jacobian, and this matrix of the Jacobian gives us the gradient also, right? This is the same thing. It's 2 times the Jacobian transposed times our function. Okay, now for the Hessian, we have now second order terms in it, right? So let's look at the diagonal of the Hessian first. So the diagonal of the Hessian is nothing else but take the function, derive it twice with respect to x1, x2, x3, and so on. So these are the second order derivatives that we're having here on the diagonal. And then not on the diagonal, we're going to have the mixed derivatives on the Hessian, right? On the mixed derivatives, we have here the function f with respect to x1, and then derived with respect to x2, with respect to x1, with respect to x3, with respect to x1, with respect to x4, and so on. So the first row here is always take the function, derive it first with respect to x1, and then with respect to wherever we are in the column right now, right? And this is the Hessian matrix. Again, I know that many of you know what the Jacobians and the Hessians are. I just wanted to reiterate it, how we actually have to compute them. And for us, what's really important always is we have to consider the dimensionalities here. So the Jacobian is always number of residuals times number of unknowns. The Hessians is actually always number of unknowns times number of unknowns. Right? So this is very important to consider. Why is it important to consider? Well, if we are now going back to Gauss-Newton, if we're going back to Newton's method, then we know, okay, this here is a square matrix, right? And we also know that this f vector has number of unknowns as rows, right? So we can, this matrix multiplication times this gradient vector actually works out in terms of dimensionality. And if you're always thinking about with respect to residuals and variables, what the dimensions of the Jacobians and the Hessians and the gradient are, then you pretty much have a good intuition already how to, well, whether you're doing things right or wrong, because if the dimensions don't match, obviously something must be wrong. Okay, now, one thing, there's a little bit of a hack now, a little bit of a complication. Often these second order derivatives are numerically hard to obtain. Right? So people say, well, it's difficult to compute a second order derivative. Sometimes the function is numerically quite unstable also. And because of that, there's an approximation of this Newton's method. And this is a method called Gaussian-Newton. So what's the difference there? Well, if this is Newton's method, or this is Newton's method, where we take the Hessian inverse times the gradient, what we're doing instead here, we're saying, well, the true second order derivatives, often hard to obtain due to numerics, computational efforts, and stuff like this, we can actually go ahead and say we're approximating the Hessian with 2 times j. All right? And in this case, this basically leaves out the true second order derivatives, and approximates it accordingly with the mixed derivatives respectively, right? And this is a thing called Gauss-Newton, and the only difference there is you're basically approximating this Hessian with 2 times JTF. So with 2 times JTJ. Okay, and Gauss-Newton then, well, now we're just taking this term here, right? We're putting here 2 times JTF here. We do the same thing, except now we have this approximation here of the Hessian, which is in principle easier to do from a numerical standpoint. Okay, so there's now a little detail that I haven't mentioned too much yet. So in practice, you're never going to invert this matrix. Especially for a large system, you would never do that. And instead what you do is you actually solve a linear system instead of inverting the matrix. So you might ask, well, how on earth do we do this one, right? Well, it's actually straightforward. So all you have to do now is we just bring this x here to the other side, or we bring this term here to the other side, right? So now we have on this side of, so well, I didn't write it down all mathematically, so, but it's very straightforward actually. So now we bring this on the other side, then we're multiplying the whole thing with 2 times JTJ, and then we have 2 times JTJ times this delta vector here. This is this vector, and then the gradient remains on the right hand side. Right? So it's very straightforward, right? So all we're doing is we're bringing this one here to the other side. We're bringing this one to that side. So it's xk minus xk plus 1. This is this delta vector. And now what we're doing is we're multiplying the whole thing, both sides, with 2 times JTJ. Then we have, on one side, we have 2 times JTJ times this delta vector. And on the right-hand side, we only have the gradient left. Okay. And now what we have to do is we have to solve, or we can solve this whole thing by solving for this delta update vector. Right? And this is a linear equation. Linear system, right? Okay, so why is this a linear system? Well, all we're doing right now is we're saying, oh, there's another thing I'm doing here. This one here is 2 times JTF. Now I can also divide by 2 here. So sometimes you see that people get rid of this 2 here. Actually, here it's wrong. Here's a 2 missing, because this is 2 times JTF. This one is actually wrong. There's a 2 missing. But what we're doing basically is now we are solving, this one is becoming, there's a 2 missing, because this one here is 2 times JTF. Sometimes people write here JTF and then they divide by 2, but here it's wrong because this is a gradient here. So there's still this 2 times JTF in there. But this one will be 2 times JTJ will become A, xk minus xk plus 1 will become x, and this one will become B. Right? Now we have solve ax is equal to b. And we can use our favorite solver that I've told you before, right? So we can use stuff like factorization method, we can use an iterative method. So this should be very clear to you how to do now. I wanted to show you a few things what we often do in our research. We often do this matrix tree, and it's pretty funny. You actually only need these 2 terms here. You need applied JTJ, and you need eval JTF. So what does it mean? Well, for instance, if you're using PCG to solve this whole thing, preconditioned conjugate gradient descent, what you do is you have like a PCG in it. I'm not going to go into all the details of PCG right now. You can look this up yourself. This is maybe not the core of this lecture. But the thing is, as long as you can, you have a PCG in it, basically, then you need to eval JTF. And at some point you have, like when you compute these conjugate gradient update steps, you need to apply JTJ. And the only thing you have to do is basically apply these 2 implement these 2 functions, and then the rest of this is all given in the library to you already. So this is something we do very often actually in our own research. And if you're interested in like GPU programming, like this stuff here can be parallelized very well on the GPU and can run very fast and very complicated problems. So for instance, we have these methods that run these bundle adjustment problems in parallel on the GPU pretty much in real time, because we get this kind of stuff very fast. So like Gauss-Newton is a very common solver, and PCG is a very common version to solve the respective linear systems. But if you're going back quickly, what's important right now is we have basically two loops in this whole thing. We have one outer loop that says compute an update step for x with this equation, and then we have an inner loop for an iterative linear system that is mostly this PCG that is solving the system respectively. So on one hand we have the outer loop of Gauss-Newton, and then we have an inner loop, for instance, of PCG or whatever iterative solver used for linear systems, or you could change this loop to some sort of other linear solve practically. Okay, yeah, this is what we're getting in practice. Okay, now there's a few variations of Gauss-Newton. I wanted to go into a bunch of them because they are actually quite relevant and super important depending on the problem you're doing. One extension to Gauss-Newton is called Levenberg. And the idea of Levenberg is you're dampening the version of Gauss-Newton. So in this case, you're basically applying you're applying a regularizer to it here that dampens the Gauss-Newton. So what this means is you just have plus lambda times I here. This is the identity matrix, and we're just adding the identity matrix to the diagonal. This is often called Tikhonov regularization. There's a bunch of theory behind it, but this dampening factor basically makes sure, like it basically tells you how much should you trust the second order approximation of Gauss-Newton at the current evaluated point. In a sense, it's kind of an interpolation between Gauss-Newton and gradient descent. But basically, what it does is like it tells you, oh, how much should I trust the second order approximation at a certain point? Right? If a function is very fluctuating with a high frequency, then you want to have a higher dampening factor. But of course, you don't just send this lambda here to a fixed value. Instead, you adapt it dynamically. So during the iterations, you're readjusting this dampening factor in each iteration. So if f of xk is greater than f of xk plus 1, meaning that my update step that I've done right now actually increased the function value, so that's good, right? That would be great. Then we just continue. If not, we increase lambda. So typically you increase lambda when this is not the case, and if this is the case, you reduce lambda, right? And this is called the trust region method. So basically what we're doing right now is we're dampening the whole thing in the area where we're looking up the gradient values or the second order values, and we're trying to figure out what's going on there. So then we're interpolating, and this is what I said already, this is basically we're interpolating between Gauss-Newton and gradient descent, right? So when the second order approximation doesn't work, we just use gradient descent. That means we have a large lambda here. And if not, we're using a small lambda. So practically you also want to use a small lambda, but sometimes if it doesn't work, then you basically have a large lambda. This is called Levenberg's method. And there's an extension to this. There's a slightly improved version. And this version means that instead of using the identity here, you can go ahead and take the diagonal of JTJ. And this makes sense because that is now scaled with the respective diagonal entries. Right? So instead of using a plain gradient descent for large lambda, you basically scale in each component of the gradient according to the respective curvature. So this basically means, well, if like the reason why this is important, if you had some components here, some diagonal entries where you have very small, or you have some very small gradients, you're basically normalizing that. So or not normalizing, but you're scaling it according to the curvature, which means you're avoiding these kind of slow convergence things when you have a small gradient in a specific component. And this is called Levenberg-Marquardt. So Levenberg-Marquardt is actually a pretty standard solver. So the reason why I introduced Levenberg is because I wanted to get to Levenberg-Marquardt and wanted to have the ideas. So right, Levenberg says interpolate between Gauss-Newton and gradient descent. This one does the same thing, except you're scaling the gradients according to the respective curvature. And in practice, this one mostly works better. And when you're using like second order solvers or so, Levenberg-Marquardt is typically the way to go. Like this is already, this is like Levenberg-Marquardt is like when somebody talks about solvers and they say, I use LM, LM stands for Lemberg Marquardt. This is well known. This is a solver that you use very often, actually. Okay, not very complicated, right? There's a few other solvers we should consider, though. There is Bfgs and LBFGs. So Bfgs stands for Broyden, Fletcher, Goldthorpe, Shannon. And this is a quasi-Newton method. And the idea of a quasi-Newton method is essentially that we are going ahead and approximating the Hessian with one-rank updates in every iteration. So we're saying, okay, the Hessian is really nasty to compute for various reasons. So what we're doing is we are trying to iteratively compute better Hessians as we do more and more update steps in our iterations. And essentially, you can think about it this way. So in Bfgs, you're basically starting with a one-rank approximation of the Hessian in the first iteration. And then every time you have another iteration, you have a one-rank update and getting closer to the approximation of the Hessian matrix, right? So yeah, and the way you do is you use this formula here. So you have this BK matrix that is being used right now instead of the Hessian, and then you're approximating the Hessian by doing these one-rank updates every time. So if you have BK that looks like this, then you have BK plus 1. Then you have this function here, which is BK plus alpha times UT plus beta times VT. So and the idea is what you do is in practice, instead of approximating BK, you directly actually approximate BK inverse, because we know it already that we need the inverse here, right? So we know how to solve eventually for it. Okay, and then there's a couple of variations of Bfgs. One of them is called LBFGs. That just means limited memory Bfgs. And the idea is that now you're keeping, instead of the full matrix BK here, you're actually only keeping a certain n. Typically, I think it's a one-rank approximation, actually. But you have an n-rank approximation that you're keeping in memory. I think practically it's a one-rank approximation, actually. So you don't have to store a square matrix. For very big problems, this LBFGs is the way to go. Actually, in practice, everybody uses LBFGs. So so if you're talking about nonlinear solves, you can use either plain Gauss-Newton, you can use Lemberg Marquardt. LM is probably the best one for the most cases. But then you have some problems where you use LBFGs, actually. BFGs I have rarely seen actually in practice being used. But the only idea is that you have a better way to store this B matrix, right? You can approximate it with a lower rank approximation, and that is more memory efficient then. Okay, so these are the main solvers that I wanted to go over. That's not everything about optimization, so don't be fooled, right? I'm not like trying to tell you everything about optimization right now. But these are the solvers that are now very important for our problems. So let's talk about this one for a second. So we want to, for instance, do Rgb bundling, right? So we have basically, again, we have frame pairs, we have correspondences between those frames, we have point correspondences here, we have transformations Ti and Tj, so we're optimizing for the T's. And this is a nonlinear squares problem, right? So T is a transformation matrix composed of a rotation and a translation. Okay, so one thing that is important, I mentioned this already, but I wanted to re-highlight this, because this might be misleading how this is written down, because it looks like it's a 2 norm and then you have 1 residual per sum, but it's in fact, it's 2 residuals here. Actually, it's 3 residuals, sorry what I said. Okay, so don't merge these residuals. And the implication here is that you need to have, for one of these terms in the sum, you have 3 residuals, one for x, one for y, and one for the z direction. That means you also have 3 rows in each Jacobian, right? If you merge these and have just 1 residual based on this 2 norm, your Jacobian would only have 1 entry there. And that would be a big problem, because now your second order solver wouldn't work anymore properly, because it doesn't know anymore in which direction you have to get the proper function approximation. And this is really critical. We have made, in many of our research problems, we have made this bug a couple of times, and if you don't do it, this just doesn't work. Like, if you want to have proper second order solvers, like or approximate versions like Gauss-Newton or Lemberg Marquardt, you have to do this one here right. Otherwise, your Jacobians just don't have the right information, the right partial derivatives in every x, y, and z direction accordingly, right? Okay, so these are 3 residuals each, and that's very important that you consider them as 3 residuals each. In the reprojection case, by the way, for bundle adjustment, there's 2 of them each, right? Because it's in x and y direction. You also need these 2. They have to be, this is really, really, really important. Otherwise, again, nothing works. Okay, so we talked about the optimization. So in principle, right, you should be able to figure out how to solve a problem like this one right now, right? You take LM, you take cos-Newton, and so on. There's a small little practical problem what you always have to deal with, and this is handling outliers. And outliers, how should I say it? Outliers are really detrimental to any least squares problem, because it's a quadratic formulation, right? If you have one outlier kills you basically, right? So that is really a big issue. So this is not so clear how to deal with outliers here. How do we deal with outliers? So what if we have this one correspondence here, what we found accidentally wrong feature match? And there's actually a lot of literature and a lot of ideas how we can deal with this. Okay, I want to give you a few hints. We can't go over all of them, but some of them I want to go into a little bit more detail. So one of them is ransack. So ransack is essentially trial and error. You basically, what ransack means is you take a bunch of correspondences. Based on these correspondences, you're trying to compute a transformation. That transformation gives you a function value for your energy. And now what you do is you just take a different combination of correspondences and you see if this function value increases or decreases. If it decreases, then you know you've done a better job in selecting correspondences beforehand. So essentially it's a trial and error, like which subset of correspondences you want to take as inliers and which ones you want to consider as outliers. And the way you do is you basically take a subset, compute a transformation based on these ones. I'll get to this later how this works in detail. The correspondence the direct computation of these relative transformations. But so you take a subset of correspondences, you try to compute a transformation matrix based on these ones, and then you take a different subset, and so on, and eventually you converge. There's a couple of variations of ransack. I gave you this one actually also as homework, so you can have a detailed look how ransack works. That's one way that typically people do when they're looking at pairwise correspondence between 2 frames. There's also lifting schemes. Lifting schemes means you're basically adding unknown variables to each correspondence, and you're jointly solving the confidence of how important that correspondence was. This one will go into a bit more details. So lifting schemes give you actually pretty good results if you do it right. They're not that easy to optimize, and they need a little bit of higher level math understanding to get them right, actually. Can't cover all of it here, but I wanted to go in this one a little bit in more detail. And the last thing is you can use robust norms. You can use an L1 norm, you can use P norms, Huber norms, stuff like that. In this case, actually also in this case, it's not a nonlinear squares problem anymore. It becomes a little bit more problematic. So then these solvers that we've just seen, they have various pros and cons depending on what kind of things you're using here. And it's a bit of a juggling act. You have to think about how difficult is it to solve it versus how well can I deal with outliers. Okay, so let's have a look at lifting schemes. I wanted to go into lifting schemes in a little bit detail. I mean, the norm should be clear, right? Instead of an L2 norm, sum of squares, you can use a sum of absolute distances. That would be L1. You can use other things here too. So robust norms should be very clear. Lifting schemes, that one you might not have heard. That's why I want to talk a bit about it. So lifting schemes, let's say we have the same thing, right? We have basically f of x is a sum of square terms. We have this issue that single outlier kills the energy due to quadratic terms. Makes sense, right? One outlier that is far away has a very large value because it's quadratic. And what we do is we introduce these helper weights to weigh down outliers. right? We want to have a high weight for inliers and a low weight for outliers. So how does that work? Let's maybe first look at this part here, at this left-hand side part. So in the left-hand side, we're saying, well, instead of just having this Ri's, we're having now Ri's times W squared I's, right? So what we would like to do is we would like to now optimize jointly for X and W. And well, in principle, the solver can now say, well, you know, if I set out, so I can basically make a decision as a solver. I can say, oh, I set a correspondence to 0. And if I set a correspondence to 0, this residual term will not count and matter for the rest, right? So take this one to 0, rule this one out. Now, a solver is not intelligent. A solver will not just say, oh, I might need that one and that one to get a good solution. A solver might just be very greedy. Whatever gets you the lowest energy, that's what the solver is going to do. And if you're only doing this what I just described with this part of the equation, and you're setting all these w's to 0, this energy will be 0. And this trivial solution is not very helpful because it doesn't give you good x values. It doesn't give you anything for your actual problem, and that's an issue. So we have to avoid this trivial solution, and because of that, we have to use a regularization term. This is what the regularization term here is doing. Regularization term just means, well, you can now set a residual term to 0, but whenever you're going to do that, I'm going to give you a penalty. So I say 1 minus w squared means if this one here is 0, then this regularization term will be larger. So if I penalize, so if I say I set a low confidence to an outlier, I will get a penalty. I will get a penalty in my regularization term, right? So my regularization term, essentially what it does, it wants to encourage to have everything as inliers, right? The regularizer is kind of this like organizes a party, it wants to invite everybody to the party and make sure everybody gets along, right? So as many inliers as possible. But some people might not be outliers, right? So you can't invite them. They're gonna crash your party. And these people who cause chaos, these ones we want to downweight. And that's essentially what the regularizer is doing. So this here is just one regularization term that you can use. It's 1 minus w squared. And this thing is called a lifting kernel. This is a lifting scheme, because what this means basically is we're lifting the variable, or we're lifting the residuals with a confidence variable that we're jointly optimizing for. And this is our lifting kernel that tells us how we treat this additional lifting variable now. So yeah, ideally at the end of the day, we would like to have all outliers should be 0 and all inliers should be 1. And now we have this juggling to do. We have to say, well, this is this regularization parameter. We have to say, oh, okay, we want to make sure that we want to have as many inliers as possible. Then you want to have a high regularization weight. So, but if this weight is too high here, then it's basically the same as not using this confidence weight at all. If this one is too low here, then I might actually reject too much stuff, because it might be cheaper for the optimizer to just set residual terms to 0 rather than finding a good and proper solution. So this is a very tricky situation how to weight these two things, and it's also a little bit tricky what kind of kernel you're going to use here. One thing to notice here, be aware, this is a sum of squares. These are square terms. This kernel that I've used here is actually a quartic term. This is a quartic term, right? Because you have a square here and I have another square on the outside. So be aware. So there's a lot of theory what kind of kernels are good, what kind of kernels are bad. It totally depends on the problem. For the most part, my understanding is you always need to have a different order of these two terms. So they shouldn't grow in the same way to make sure the optimizer can find a better optimum. Okay, so that's something you can do, and this works pretty well if you're doing it right. It needs a little bit of juggling of these regularization terms, like what kernels and also what regularization parameters to use. Okay. Now let's maybe talk a little bit also about robust norms. So one thing I already mentioned, instead of treating this as a least squares problem, you can have a p-norm here. P could be 1, for instance. What we could do here is we could go ahead and take an 1 norm in order to find a better solution that's not so sensitive to outliers, right? Same idea, you have a p-norm here, you're finding an optimal x with respect to this argument. This is a thing from an optimization perspective that is not so easy to do anymore. So if you just, you can't just dump this into a Gauss-Newton right away. And the way you do this is you basically treating a problem locally as L2. And this is called iteratively reweighted least squares, IRLS. This is a very common term that people use in this area because this is very straightforward to do. And what you do is basically iteratively solve the whole thing. So you say, well, I'm going to have a function f of x. We know it's a p-norm. But what we do is we just say, we're treating it as some part of this residual is a square. We're just factorizing this one out. And we're having a part of it that is missing right now in this term to make it a p-norm instead of a 2-norm. So we're factorizing that one out in this wi. But what we do is, so wi is basically nothing else but whatever is missing to the p-norm, right? So wi times ri squared is the same as ri with the p-norm, right? So this is ri p minus 2 norm, right? It's very straightforward because if you multiply the 2, then you're getting to the original term. But now what you're doing in this IRLS solver, you iteratively solving it, and you're basically fixing this wi for the current iteration to make it tractable with a nonlinear square solver. Like, right? Now we can use Gauss-Newton again to solve this one, and then we iteratively update it again. This is often called fixed point iterations too. So if you are interested in that, if you look up fixed point iteration methods, that's basically one version of it. And this works actually remarkably well, for instance, for 1 norms and so on, right? So this is a thing you should keep in mind when you want to deal with outliers. This could actually help quite a bit in practice. Okay, couple of other things optimization-wise, local versus global minima. That's a big problem when you're dealing with RGB terms. If you have two RGB frames, you want to align them in a dense framework. Very, very difficult, right? So one thing people do often is you do convexification. By the way, that's a thing you always want to do when you do any optimization. You always want to do things like coarse-to-fine strategies. Basically, hierarchical optimization, it's not only faster, but it also helps you to get better optima. So convexification here means you can go ahead, for instance, and blur the images and reduce the resolution of the images. That's smoothing it. You can do coarse-to-fine over the unknowns, but you can also do coarse-to-fine over the residuals. So like downsampling the images is coarse-to-fine over residuals. Coarse-to-fine over the unknowns would be I just take a subset of the frames, have a bunch of keyframes, optimize over keyframes first, and then locally optimize in a bunch of chunks of keyframes, right? So this is something you can do. And in practice, you always want to do that actually. Like if you want to be reasonably fast, you want to do it, but also if you want to regularize the problem a little bit more, you want to do this. So local minima versus global minima is very important. You have to consider that convexification, making landscapes smoother and more convex. Maybe I should have said more convex because they're still not perfectly convex. But with good initializations, we can actually make it tractable for the most part. Okay. Couple of performance and efficiency considerations. Well, we talked about the Jacobians, right? We have variables times residuals here as a matrix dimension. And we basically have to check out in Gauss-Newton, right? We have to solve this linear system, so we have to solve for these ones here. There's the sparsity of J that has to be considered. So if J is sparse, that's easy to solve. But basically, how many unknowns, how many residuals directly affects the dimensionality of J, JTJ, and so on. And this is like very important. Talking about PCG, also very important. If you're doing applied JTJ, there's this interesting little detail. So in this term here, when you compute these conjugate gradient updates, there's this fun thing. You have like 2 times JTJ times PK. pk is the previous update vector, basically. Sorry, the previous direction of the update vector. And now the interesting thing is you can do jtj first times p, or jt and then times jp. Depends totally on the problem which one is the best version here, and how you parallelize it on the GPU and so on, for instance. So that I just wanted to explain that you should go in a little bit detail and like really think through like how you would map this into your actual solver. So this is really important if you want to be fast and efficient. Okay, so that's pretty much it for right now for the theory behind the solvers and the optimization. Now I would like to talk a little bit more about computing derivatives. I might not have all the detail there, but I wanted to give you at least a bit of a hint how you do this in practice. And all of the solvers we have talked about right now, they're all derivative based, so we have to compute derivatives in one way or another one. If you're computing derivatives, when I think about it, I think about a whiteboard and I have to do this myself, and I just write it down and I make a bunch of mistakes, and then at the end nothing works anymore. So I would like the computer to do this for me, right? So I would like to have some way such that these derivatives are computed in some sort of automated way. Essentially, there's three ways to do that. There's numeric derivatives, automatic differentiation, and symbolic differentiation. All of this have advantages and disadvantages. Let's talk about numeric derivatives first. That's the easiest thing. Basically, these are central forward differences, straightforward, right? All you're saying is, well, you just say, oh, you look at the current slope of your derivatives in the current direction, right? So you say, oh, I have f of x plus h minus f of x divided by h. That gives you the local derivatives, and you're making h relatively small, numerically small, right? So you're just saying h is a small value. How small? Who knows, right? That depends on your implementation on your problem. Central differences is the only difference you say x plus h and x minus h. These are a little bit more stable. Yeah, but similar idea, right? So these are like numeric approximations. So basically what you're doing is you're kind of sampling locally the function in order to compute based on these samples a local gradient. And forward difference, central difference is the easiest way to do it. Really easy to implement. Very good for debugging. Pretty much I think every solver library has one way of numeric derivatives. But they're super slow to compute, right? And like, why are they slow to compute? Well, if you have a Jacobian matrix, right, you have to do this kind of stuff a couple of times for every partial respectively, right? And that's a lot more expensive than having an analytic version of it, of course. Okay, this is slow, numerically also super unstable. Like, how on earth do we change this h that it does something good? You have to basically try it out depending on the problem formulation, right? There's not much else you can do. There are some things, but practically speaking, it's a difficult situation. Okay, so numeric derivatives, again, easy to do, but if you actually want to do something fast, numerically stable, it's not the right thing, but it's for debugging purposes, it might be still pretty good. Okay, there's a thing called auto differentiation. Actually, there's many ways to do auto differentiation, but I wanted to show you one thing that I found pretty cool. One thing that is really cool is using dual numbers. So the idea is if you have a function f of x is equal to x squared, what you can do now is you can choose an infinitesimal unit e such that e is not 0, but e squared is 0. Right? This is just a made-up number. And this made-up number, they're called dual numbers. It's similar to complex numbers, except that like e squared is 0 and e is not 0. And the idea is, if you're having a function right now, you just say f of 10 plus e, so you just add this e here. This is your dual number. You just keep track of the dual number here. Is equal to 10 plus e squared, which is the function we have here, right? This is x squared. So it's 10 plus e squared. You have 10 plus 2 times 10 times e plus e squared. And now the interesting thing is, this square term here is 0 by definition. And this term here, what's left of it, is the derivative, which is funny, right? And this works remarkably well. You can try it out. And this is cool, right? So basically, the function, this x squared function, if you want to evaluate it, at 10, your derivative will be 20. And you know that, right? Because the derivative of 2x squared is 2x, right? So 2 times 10 would be 20, so we know this is the derivative of x squared at the value 10. This is the dual number. It's straightforward to do. You should try it out. It's very easy. And this is actually what Celeries is doing. Celeries is a solver library that I can only recommend. And you can implement this with chats. What are chats? Chat is just a C++ construct how to implement dual numbers. And the idea is you just say you keep track of this dual number part, right? So you have always this template here. This chat struct here is templatized, and it basically has the scalar part TA, and it has the infinitesimal part v in this case, right? And now the only thing you have to do here is you have to overlay this operator when you do multiplication. Obviously, you have to do it for the other parts too. And now for your operator, you know when you do multiplication, you know that you have f and g here as input, you have h here. And h point, you have to basically from h is your return value. So you have to compute a, which is the scalar part, and v, which is your infinitesimal part. So for the scalar part, it's straightforward. You just multiply the two scalar parts of your inputs of f and a. And for the infinitesimal part, you just compute the respective derivatives, right? So it's f times a times the infinitesimal part plus f times f point v times g dot a, right? And then you return it. And you just overlay this for all the operators respectively. This is for the multiplication operator. And then you have this kind of stuff being abstracted away through the dual numbers in these chats. And this is kind of cool because once you've done that, you have full auto differentiation. That's very nice. Okay, so good thing about that one here is it's very generic. It gives you good results. It might be a little bit slow sometimes depending on what the compiler is doing in the template magic. It depends a little bit. And to get that intuition, I wanted to go to the last part of the differentiation, which is symbolic differentiation. And the idea here is you can analyze the compute graph at compile time and then simplify and fuse the terms accordingly. So how well this is like fused and simplified totally depends on the template magic of the compiler. But if you do symbolic differentiation, you can basically do this by hand. So you just say you have some expression, right? And based on these expressions, you compute this compute graph. And based on your compute graph, you compute the derivatives offline first, and then you do some simplification step, which gives you a good answer. This is close to, oh, let's do it on a whiteboard, but rather let's have the computer do it for us, and then do it yourself. And then let the simplification happen. The simplification, by the way, is NP-complete. It's not so straightforward, but there's a lot of heuristics to do it well enough, basically. And yeah, this is like, ideally, you always want to do symbolic differentiation, but it depends on the compute or the programming abstraction that you're using, whether it's actually doable. Okay, we have a couple of solvers I wanted to point out. Celeries I already mentioned. Celeries is a really cool library, I think. I used it a lot. It uses eigenS backend. It also has a PCG backend of its own for the linear solves. It uses automatic differentiation using these dual numbers. Check out this chat.h file. I think this is kind of cool. Again, you will learn a lot about programming. And this makes it fantastically easy to use and also pretty efficient, actually, from a compute perspective. Okay, there's other solvers. Outlib is one I've used a couple of times. The C++ library that does numerical differentiation, or you can provide hand-provided gradients. Basically, you have to provide the Jacobian matrices, so you can do it on a whiteboard. But they implement basically Lemberg marquardt. Yeah, Celeries is also Levenberg marquardt solver. But then there's symbolic solvers. Maple is a good tool. Maple is good for like theory and trying out stuff, kind of like a whiteboard, but you want a computer to help you with the difficult derivation stuff. Not so great for code conversion and simplification, but very good for symbolic differentiation, actually. There's many more. This is just a few examples that I had a look at, but again, there's many more. Okay. Introduction to Celeries. I'm running a little bit out of time, so I hope you will have a look at Celeries on your own. Like, Celeries is a really, really powerful library. If you ever want to do like research with it, you just have to understand this kind of stuff. But the idea of Celeries is straightforward, right? So the idea is you have a cost functor, and what you do is so this is the main part of the code here, right? So you have a cost function, and what you do is you just create an additive cost function. You put in the template. This is a function template of this function. And the idea here is that you have to operate, you have this parenthesis operator basically of this function you're overloading that gets you parameters and residuals as input. In this case, we have a 4-dimensional residual input. You have 4 parameters, B1, B2, B3, B4, and this one computes 1 residual right now, and this is 1 residual, 4 parameters. What this means is now we have these parameters here, and then what we're doing is we're just computing the function here, which is this function, right? And then you're just writing this one out as a residual. And what this means now is Celeries now knows for this function, the function gets x and y respectively. These are the points that you want to fit it to. And now what Celeries knows how to do is it knows to compute the derivative of this function. Why? Because it has this chat.h, and through this chat.h, out of this computation, because all of these parameters are overloaded, right? Sorry, all of these operators here are overloaded. Because of that, it computes these dual numbers of these terms here, and then it keeps track of the dual numbers internally. Okay, again, note the templates. That's very important, actually. Yeah, note the templates. Okay, so I want you to have a look at this one. I think this is very instructive if you're trying it out yourself, actually, and coding it up. But then you also, based on what we have learned now in this lecture, we should know how can we use these kind of things and what they do under the hood, actually. Okay. I wanted to mention a few things to deep learning. There's a huge connection of these solvers, what we have been doing today. And I want you to make sure that you don't confuse them. So deep learning uses a gradient-based solver. Specifically, they use stochastic gradient descent. There, the idea is they don't compute the full gradient, but rather approximate the gradient based on a bunch of samples. The backpropagation computes the actual gradient. There's a bunch of frameworks how to do this. The additive frameworks are like how this is implemented, or like the layers implemented yourself already. They don't typically use second-order solvers. The reason why the stochasticity is used is because for large training sets, the true gradient is computationally expensive if you have large training sets. And because of that, they use this stochasticity. And there's also a lot of theory why that helps with local minima, which local minima is useful, and then like how different local minima correlate to other local minima. Like for instance, in neural networks, you often have many local minima that are equivalent in performance, even though the weights are different, and so on. And what turns out is this stochasticity doesn't go well with the second-order solvers. There are attempts. Maybe people will figure it out, but right now I don't think they work so well yet. So people at the moment still stick to SGD variants. In terms of the deep learning frameworks, a lot of them operate on compute graphs. Backpropagation, i.e. computation of the derivatives, is done by applying the chain rule, so they keep track of the derivatives. And then the deep learning frameworks, I mentioned this already, they support some version of additive, like AutoGrad in Torch PyTorch. And in practice, when you want to do some fast prototyping, you implement only the forward pass in your layer, and additive figures out how to do the rest for you. If you want to do really fast stuff, and for instance, if you have a ConvNet or so, in practice, the layers still have handcrafted implementations because they just work faster. And for important layers, people have a good motivation to do it faster, because then suddenly training time is, rather than a month, it's just a few days. So sometimes that makes sense. But just saying, like, they have AutoGrad versions actually that are really, really powerful and cool. Okay. few other things, connections to other optimization methods. I think there is hard and inequality constraints that are very powerful. Lagrange multipliers are being used often there. ADMM, alternating direction of methods of multipliers. Primal dual methods are being used. These hard and inequality constraints is not something we talked about at all right now. So I just wanted to make sure that you know, oh, we're not dealing with generic solvers here that can do anything. We specifically talked about nonlinearly square solvers today. There's also gradient-free solvers, Monte Carlo methods, Metropolis-Hastings is very populated, simulated annealing, genetic and evolutional solvers. Didn't talk about these ones at all. Gradient-free solvers is a blessing and a curse. They are very generic. You can throw them at pretty much everything. They can deal with non-continuous functions, even when you can compute any gradients at all. But in practice, they're sampling-based, which means they are practically very, very slow. But yeah, and then there's differentiable equations, right? Like if you're talking about like physics simulations and so on, PDEs, ODEs, stuff like that. A lot of literature there too. Also, we didn't touch that. The reason why I'm mentioning this here is I just want to make sure that we have talked about a very specific set of solvers today. There's a lot of other different solvers we haven't talked about. There's a lot of theory around it. We won't touch these ones because practically they are, for our problems right now, they are not the most relevant ones. But I still want to make sure that you have kind of this big picture overview that, hey, there's other stuff too. And like your answer is not everything is gradient descent, right? It's just a bad answer. Okay. Good. So now what we should know how to solve these nonlinear terms, right? We should know how these bundle adjustment and Rgb bundling methods should work. We also should know in the RGBD case how we do frame-to-frame alignment, right? If you only have one frame pair, we should be able to align that. We will talk now a little bit in the next lectures about ICP and these kind of things, like iterative closest point. This is one of the next things we're going to talk about, but I think right now you should have a solid math background that we can solve most of these problems. Okay, so I have a little bit of a homework for you. One of the homeworks I mentioned, look at Celeries, look at the documentation of the order derivatives, try to solve your own toy problem, run some base code maybe. They have a few samples there, how you can run it. It's very straightforward to set up. This is one of the homeworks. And the other part of the homework, I would like you to have a look at, do some literature research around RANSAC, try to understand how RANSAC works and what the key ideas around it are. Okay. And next week, as I mentioned already, we're going to go into tracking rigid surfaces. And then finally, we talk about a little bit more reconstruction. And we're going to use a lot of the math we have learned and heard about today. Okay, so see you next week, and thanks a lot for tuning in.